This task requires the design of an algorithm in n log n time, which takes an integer x and a set S of n integers and determines whether there exist two elements in S that sum to exactly x. There are two cases which allow us to quickly rule out a solution. If x is less than the sum of the two smallest elements, or if x is greater than the sum of the largest two elements. If x is anything in between this, a solution could exist. So this suggests that the set of elements should first be sorted to eliminate the two mentioned cases. Now, any sorting algorithm could be used, but in order to keep the time and space complexity of this algorithm to a minimum, merge sort would be a good choice, as the best, worst, and average complexities are all n log n. So now that we have the set of elements S sorted, let's look at how we can find our two potential elements. The algorithm involves two counters, one starting on the left, the smallest element, and one starting on the right, the largest element, because remember now this list is already sorted. We add the two elements together and we compare their sum to our element x. If the sum is greater than x, the right counter is decremented one element to the left. If the sum is smaller than x, the left counter is incremented one element to the right. If the sum is neither smaller nor greater than x, then it is equal to x, and the algorithm will turn the two values. So let's just look at an example and see how it works. So our element x is equal to 100. So our counter on the left is at 14 and right is at 108. So we sum these two together, which gives us 122. And we check if the sum is greater than x, which it is, so we decrement right. And now we have 14 and 93, which is 107. Again, we check, this is greater, so we decrement right. So now 14 plus 73 is 87. Oh wait, this time it's less than x, so we increment left. And now we're on 23 plus 73, it's at 96, it's still less than, so we increment left again. Now we're over, so we're at 120. So now we decrement right. And we're at 114. We're still over, decrement right one. And now, look, we're at exactly 100 and the two numbers are returned. So we found our two elements. But what would happen if there were no two values that sum to x? What we would need is a way to stop the loop before the two counters referred to the same element. So we wrap the loop in a condition. But let's also add in those two initial checks, which means we also need to add in the sorting algorithm. So let's analyze the complexity of this algorithm. We can do a thorough analysis of every line, like this, but it isn't really necessary. What we need to find is the high order terms, as constant and coefficients are generally insignificant when it comes to large input values. And looking at our algorithm, we have the sorting, which runs in n log n, and then we have one while loop, which is on the order of n operations, bringing this algorithm to close to n log n plus n operations. Again, since when it comes to large inputs, only the highest order term is important, and in this case that is n log n. So our algorithm performs with time complexity of n log n.